Well, hello, and I'd like to talk to you now about diagnostic testing in individuals with Dravet syndrome. And I've just spoken about the electroclinical presentation of Dravet syndrome and created this puzzle to show all the different features that one needs to think about. But the final important piece of the puzzle is looking for a cause, and for Dravet syndrome, this is genetic. So the sorts of genetic testing that we can do in 2022 begin with exome sequencing. Now, sometimes you can just get an epilepsy gene panel, but in reality, many of the companies are actually using an exome and just looking at specific genes. Whatever the case, it needs to be some form of next generation sequencing. In Australia, in the US, and in many parts of Europe, there is a no-cost gene panel called BehindTheSeizure.com, which you can use for any child under the age of 8 years with afebrile seizures. Now, that can be an issue with Dravet syndrome because they can have just febrile seizures. But as soon as they have an afebrile seizure, if you're in the right region, you can have this testing at no cost, and they will also look at parental segregation. If you've done an exome and it's negative, then the next step would be a genome. At the moment, this is largely in the research domain, but it is increasingly being used clinically. If that's normal and the exome's normal, one must always make sure that you've done a chromosomal microarray. This is to detect copy number variants, such as deletions or duplications. These should theoretically be picked up by genome sequencing, but will be missed by exome sequencing. Now, there is increasing interest in looking for rare intronic variants in genes known to cause a specific disease. And this is just beginning to bear fruit in terms of specific types of intronic variants. Now, critical question for your patients with Dravet syndrome is, who should you test and when should you do it? Well, I think it should be as soon as you think about the diagnosis of Dravet syndrome. If it goes through your head, that's a good enough reason to test. With a baby, it will usually be with their first seizure or their second seizure, particularly if they're slightly prolonged, say more than 5 minutes, if it's a generalized tonic-clonic or hemiclonic seizure with or without fever. But what about the adults? There are many adults who have Dravet syndrome that has been missed. The key to diagnosis in an adult is to get their early history. If their parents are no longer around to give that to you, then write to the hospital where they were seen as a baby and get the notes. Because when you read it, it will often read just like a textbook and you go, oh, they've got Dravet syndrome. And then you should definitely organise testing. Why? Because it will change your management today. And there's a beautiful example in the Caterino et al. Paper in 2011 where they tested 60-year-olds, and by stopping carbamazepine, they found that they improved cognitively and they could improve their incontinence. So most of the action in Dravet syndrome, more than 90% of patients have a pathogenic variant in SCN1A, and that encodes the alpha-1 subunit of the sodium channel, which you see here. It forms the ion channel pore through which the sodium ions pass. And here you can see it embedded in the cell membrane with the beta subunit, which is important in channel gating kinetics. There have been many, many studies of Dravet syndrome genetics now, with well over 2,000 pathogenic variants described, with many patients having novel rather than recurrent pathogenic variants. The take-home message is that more than 90% of individuals have a pathogenic variant in SCN1A, and that 40% of them are red or truncation mutations, and 40% are blue or missense mutations. There are other types of mutations you can have, such as splice site mutations, intronic variants, copy number variants, and structural rearrangements. Now, I mentioned before that genome sequencing is beginning to give us new insights into the molecular genetics of Dravet syndrome. And one of the things that we found with Gemma Carville some years ago is that with intronic sequencing, she found this very small poison exon. And we found 5 individuals with mutations in the region of this poison exon, suggesting that if you have a mutation here, you actually end up with aberrant SCN1A inclusion of intron 20N, and this produces a truncated protein, which results in SCN1 haploinsufficiency and Dravet syndrome. But this was a tiny exon that was missed until the days of genome sequencing. I wanted to turn now to the inheritance of SCN1A mutations. 90% of patients have a de novo pathogenic variant, which is present in the child and not present in the mother or father. There are, however, a lot of patients who may have mosaicism. And mosaicism is illustrated beautifully by this Australian Aboriginal Indigenous artwork of a lizard, where you see different types of cells in an individual. And to look at a more scientific image now, you can see here an example of somatic mosaicism. So the baby forms normally, and as the zygote divides, you have a pathogenic variant that occurs somewhere along development. If it's towards the end of development, it will just be in the brain, but it may be here, and then you may have a low level of mosaicism through the body. Now, the other type of mosaicism is where it's a germline mosaicism, and this might be where you have an unaffected parent who has it limited to their gonads, their either eggs or sperm. And as you can see, they're normally wild type or blue, but they may have just one cell initially harboring the mutation. It divides, and then it's localized to a certain part of the body, or maybe at low level in blood and saliva. Now, obviously, if that egg or sperm has that mutation, it will be in every cell in the baby's body, and they will then have the disease of Dravet syndrome. So thinking about the first example, what about patients with Dravet syndrome? Well, this is an elegant Dutch study from Bobby Coleman's group, where they looked at 113 patients with Dravet syndrome with SCN1A pathogenic variants. They looked in each patient 1,000 times with deep sequencing of the mutation, and they found that 7.5% of the individuals were actually mosaic. If they had a truncation mutation, they had milder features than if they were truly heterozygous. Now, this finding has important genetic counselling implications, because if it's new in the child and has occurred after the zygote has developed, the parent cannot carry it, and therefore they are not at risk of having a second affected child. Turning now to the second type of mosaicism, where it's in the parent rather than the child. Once you have 2 children with Dravet syndrome, it's obvious that one of those parents must carry the mutation. And in this family, a father had a history of febrile seizures, and he was 28% mosaic for his children's mutation, but both children were severely affected, and this girl later died of SUDEP. In this family, the mother was 17% mosaic and had febrile seizures, was very normal, and she fortunately only had 1 child with Dravet syndrome. So speaking more broadly, reproductive counselling in the developmental and epileptic encephalopathies is essential. And this is because the frequency of parental mosaicism has been underestimated. We found that 8% of 120 trios, that the child had a parent who was actually mosaic, and this would significantly increase their risk of having a second affected child, as you can see in this family here. A red flag to parental mosaicism is if the parent has seizures such as febrile seizures, and if they had a higher percentage mosaicism, then they were more likely to have more significant epilepsy. So here we have mosaicism in the child and mosaicism in the parent. And the third form of inheritance is when the parent has got it and is heterozygous, but will be mildly affected, such as with genetic epilepsy with febrile seizures plus. And then the question is, why is the child more severe? And the answer is likely to be here that the child must have other modifying genes. But this is not the whole story. If you look at this elegant study from the Zuberi-Brunkhaus group, they looked carefully at other genes associated with the Dravet-like phenotype. And one of the ones that was first championed as being Dravet-like is actually fairly distinct when you get your eye in. PCDH19 is characterized by clusters of seizures, often triggered by fever, but usually brief seizures. So some of these can look a little bit like Dravet syndrome, but SCN1A is really the main one. So in conclusion, this is our Dravet puzzle with all the important phenotypic features for Dravet syndrome, and the molecular genetics show us that more than 90% have a pathogenic variant in SCN1A. Thank you very much for your attention.